Hey guys, Buildzoid here, and today we're going to be doing a PCB breakdown of the ASUS R9 Fury Strix. And you might be sitting there going like, Buildzoid, it's 2021, why are we looking at an R9 Fury Strix? Well, it's very simple. I finally got my hands on one of these. More specifically, I got my hands on a Revision 1.0 card, and so I finally know what power stages it used. So yeah, and also since I have one, I want to talk about it. Anyway, before we get to the card more, the pictures are from Tech Power Up's review of the R9 Fury Strix because they're better at taking photos at me. So thank you to Tech Power Up for providing high-res PCB pictures in their GPU reviews. And with that out of the way, let's get into it. So I guess let's start with how I ended up with one of these. So I've wanted an R9 Fury Strix for a while because I have a Nitro Fury, I have a reference Fury, I have a bunch of Fury cards, and sort of within my, I really wanted one of these mostly to compare it against the other Furies I have. And I got one on eBay for around 55 quid because as 4 parts for not working. And the reason it was not working is because something went wrong with this BIOS chip over here. And ASUS, in their infinite profit maximization ways, doesn't include dual BIOS on this card. But, you know, like, they have the switch for it. But yeah, the card does not ship with dual BIOS functionality. And so, yeah, I got really lucky because the card that was listed on eBay, the only thing that was wrong with it was something with the BIOS chip. I don't actually know if the BIOS chip was dead or if it just had a dodgy BIOS on it. Basically, I desoldered the BIOS chip, replaced it with a BIOS chip off of a Fury X, then flashed it back to an R9 Fury Strix BIOS, and I now have a working R9 Fury. If you're wondering about the symptoms that the card had when it showed up, when it was trying to boot up, it would just get sort of stuck at 1.1 volts on VCore, 1.1 volts on HBM, and 1 volt on VDDCI. Which is kind of interesting in the sense that normally AMD cards boot to 0.95 volts, but I think ASUS has a different configuration for the default boot up voltage on the VCore, on like the main controller on this card, which would explain why it boots up to 1.1 volts instead of 0.95 like you normally see. And actually, I think it's 0.9 or something. Anyway, like it boots to like suspiciously high voltage compared to most Furies. And the other thing is that the card wouldn't let the system initialize even if I install a second card into the system to get display out, because obviously this thing didn't put out an image, which is why it was on eBay. But yeah, if I put another card into the same system as this card, it would get stuck in the post process, which made me think, okay, this card seems to be causing some kind of initialization issue, which is probably caused by the BIOS. So remove the BIOS chip, replace it with a known good BIOS chip off of a dead Fury X that I have, and flash it back down to a Fury. Ta-da! I have a working Fury Strix now. So that's how I got one. So thank you, ASUS, for screwing over your customers by not including basic functionality like dual BIOS. Especially for high-end AMD GPUs, dual BIOS is like a staple feature of even the reference cards, at least until recently, because I guess AMD came to the same conclusion that ASUS did, which is like, you know what, that switch and that BIOS chip, very expensive. We can't afford to include that on these cards anymore. But yeah, like if you go all the way back to like the 5870 reference card, it has dual BIOS, if I remember correctly. 6970 reference card has dual BIOS. 7970 reference card has dual BIOS. Even 7950s have dual BIOS. Like, basically every AMD GPU for a very long time now, until I think the 5700 XT, would come with dual BIOS as standard. And then AMD just sort of stopped doing that, so that sucks. But here ASUS didn't include dual BIOS, and thanks to that, I managed to get a Fury Strix for 55 quid instead of over 100, which is what a lot of them end up going for on eBay. Admittedly, those are working, but yeah, so saved a bit of money. I still think paying 55 quid for a not working Fury is a bit too much, because if I got unlucky and it wasn't the BIOS chip, like the main concern with these cards in terms of things that die on them is, like, if somebody cleaned off the thermal paste a little bit too aggressively around the die, it is trivial to destroy the interposer, because you have this, like, exposed section right here, and basically, if you just apply too much pressure to it with a hard enough object, dead card. So when I clean these, I actually don't clean this area at all. Like if there's thermal paste here, it stays. I am not touching that because that's why I have a dead Fury X, is I was a little bit too heavy on the cleaning procedure when I was replacing the thermal paste, and then it's like, oh, now the card is permanently artifacting. How great. Awesome. Lovely. Um, so anyway, so that got turned into a parts card, and now bits and pieces of it live on in other GPUs, like the BIOS chip on my Fury Strix. Anyway, let's talk about the power delivery on this thing, because this is actually the most custom Fury PCB that you can get, which is one of the main reasons I wanted it. Most Furies that you can buy just use the reference PCB, which is the same as the Fury X. And then ASUS over here actually has 2 revisions of this card. I think we'll do a video on the second revision of this card as well eventually. But I only have the 1.01 revision of this PCB. I don't have the 2.0 revision of the PCB yet. The 2.0 revision is, well, really hard to find. I don't know how many they made of them, but yeah, it's like, there's no, the other issue is the revision number, this right here, it's under the back plate. So if somebody, like, if you see pictures of the card on the internet being sold, you have no way to tell which PCB revision it comes with. But anyway, yeah, let's talk about the power delivery. So this right here is the VCore, and I'm pretty sure this is the most powerful VCore VRM other than the revision 2.0 that you can get on a Fury or Fury X. Just, you know, like, I don't really make much of a distinction between the two because a lot of Furies will actually unlock into the same core count as Fury X's. And anyway, so this is all VCore over here. And then over on this side of the card, we have the HBM rail down here. So that's the HBM power. Then above that, we have the VDDCI rail. And down here, we have the 1.8 volts and the 0.95 volts. I'm not sure which one's which, so I'm just going to put the label over here, I guess. And so this voltage is super useful for LN2 overclocking. It might even help at ambient. Basically, a lot of 28 nanometer AMD GPUs, especially the bigger ones, have a very real problem of dropping display outputs at high core voltages and high clocks. So one of the fixes for that is you just start raising the 0.95 volts rail, and hopefully it goes away. Also, the 0.95 volts rail helps with getting AMD 28 nanometer AMD GPUs to run at lower temperatures. So a lot of the 28 nanometer AMD cards, they will like cold bug at like minus 100. And by increasing this voltage, a lot of the time you can get them to much, much lower temperatures than that. Yeah, unfortunately, I'm not sure which rail is which. The 1.8 volts rail is, I believe it powers like the BIOS chip, and then it also is a supporting rail for the HBM. And generally speaking, this rail doesn't do anything. Like, you don't need to worry about it. It exists, and that's the, like, it's important if it doesn't work, but otherwise it's just kind of like, oh yeah, there's a 1.8 volts. That's a thing. So that's what those two regulators are for. VCore and HBM are handled by this chip over here, which that is an ASP 1300, which I suspect is a IR3567B rebrand. The IR3567B is the standard voltage controller for R9290Xs, R9290, like a lot of AMD GPUs. Including Furies, Fury X's. I think RX 480s also use the 3567B. Nice high-end up to 6+. I can't remember if it's a 6+2 or a 6+1. I think it's a 6+2. Yeah, multi-phase controller from international rectifier up to 2 megahertz switching frequency. Not that you would ever use that unless you have a lot of unless you had like quadruplers hanging off of it in actual quadrupling mode. You know, in that case, you might want to run it at 2 megahertz so that you get 500 kilohertz at the actual phases. Yeah, anyway, here the ASP 1300 is running as a 5+1 configuration, with 5 phases going to the 10-phase VCore, and the other, there's doublers on the back of the card, and the other 1 phase going over here. And this is a really interesting thing about a lot of ASUS GPUs from this sort of era, and I think I figured out why they do this at this point. This chip over here is an IR3598, which is really not what you would expect to see on a single-phase HBM rail. because the 3598 is actually a dual driver with a doubling function. So you can feed one PWM signal in, or you can feed two PWM signal. Like, if you feed two PWM signals in, it'll do two independent phases. It's literally like two driver chips in one IC. But if you feed one PWM signal in, you have the option to set it into into doubling mode, and it'll actually spit out two phases, which is pretty cool. However, it doesn't make any sense to use a 3598 on a card like this, where, you know, you have a single phase HBM rail, except I suspect what's going on here is that ASUS actually was using these 3598s a lot on their other GPUs at the time. Like, you'd find DirectCU2 cards would have 3598s for VCore. Like, they just have 3598s all over the place. I think they used 3598s on motherboards. So I suspect ASUS just had piles and piles of 3598s. And instead of getting like a CHL8510, which is what you would normally see as a single phase VRM driver, like MOSFET driver for international rectifier controllers, they just kind of keep using the 3598 even in places where they don't need that, you know, second driver function that these chips offer. So yeah, we've got a 3598 handling the HBM MOSFET drive. The doublers on this card are here on the back. So, you know, we've got 5 of them. And these are all IR 3599s. So these can also quadruple. Obviously, that's not being used here. They're just running as a doubler. So what happens is you get, say, a 500, like if you have a 1 megahertz signal goes in, you get a 500 kilohertz signal coming out to the two phases. And then the IR35, and then the actual voltage controller, assuming that this is actually an IR3567B, which it almost certainly is, will actually, because the thing is, the 3599 is like a really dumb doubler. Like, it just takes the PWM signal and like switches it between the two phases. Whereas, and the problem with that a lot of the time would be that you wouldn't actually have like a way for the controller to distinguish with which phase is which. However, the 3567B is so advanced that through the current sensing circuitry, it can actually tell when it's going through doublers, it can actually tell on its own which phase is handling how much current through its own current sensing circuitry. There's a lot of other controllers where they'll actually require a doubler that does the current balancing for the controller. With the international rectifiers, international rectifier controllers, the controllers actually can distinguish between the two phases, even if they're in a doubling scheme like they're here. So anyway, oh, and I guess since this is an ASUS card, we may as well mention that having, you know, doublers does slightly delay the PWM signal, which can lead to slightly worse transient response, to the extent that if you just have enough capacitors, it doesn't really matter. So anyway, yeah, so that's the control scheme for the VCore here, is just 5 phases into a bunch of 3599s, and then that goes into 10 phases of MP 86905s. Now, these are monolithic power systems, so MPS, which, like, best component manufacturer name ever. Monolithic power systems, like, what a name. But anyway, so MPS, MP86905s, these are 50 amp power stages, and actual power stages, not like DRMOS. They have thermal monitoring built in. Do they have current sensing? I think they have current sensing built in as well. We're going to the back of the card because I want to check if the... I should have just checked the data sheet for this. Yeah, I'm pretty sure they have current sensing. I didn't pay that much attention to... I should have read the documentation more. And anyway, the crazy thing about these is even though they're nominally only 50 amps, they have insane efficiency. Like, they're on par with like 60 amp or even 70 amp parts. So these things are absolutely ridiculous. And in this 10-phase configuration, what that means for this VRM is that at 1.2 volts output voltage with a 500 kilohertz switching frequency, 200 amps output should only be producing about 16 watts of heat on the actual power stages, which is, like, that's in line with what you would expect from, like, really, really high-end power stages these days. Well, actually, there hasn't been The thing is, like, we now have like up to 90 amp smart power stages, you know, in existence, and the thing is, they're not that much more efficient. Like, there's a very slight improvement going from like the 70 amp parts to the 90s, but yeah, these things which are nominally 50 amps, so I guess they just have some kind of like there's a different the limitation with these probably isn't the efficiency, maybe it's just of the actual like internal silicon in these, it's probably the packaging or something that just can't handle that much current. But yeah, like within their optimal operating range, like the efficiency on these is absolutely ridiculous, comparable with like 60 and 70 amp smart power stage parts these days. So really, really cool that like ASUS was using these of all things. Yeah, 200 amps, 16 watts, 300 amps output. You can expect about 31 watts of heat, which again, like for 300 amps output, that's great. Like it's not, like, yes, there are VRMs that do better than that. Not in like 10-phase configurations. You'd be looking more at like a 16-phase or something to go much lower than 31 watts at 300 amps output, but still like really, really good. And then 400 amps output. And I guess that, yeah, must have been they start producing about 55 watts of heat. So I guess that's the main difference there, is that actually I should have put more time into like researching this video, because I have a sneaking suspicion that like a 60 amp part would do better at 400 amps than this does. Not necessarily at these two. Like 60 amp parts in this VRM would probably have the same or worse 200 and 300 amps, but I think 400 amps, this is actually kind of high. Let me check. Screw it. Like this video, yeah, this video is going fine. It's not going to end up... So far, this video is doing great. Let's destroy it. So let's do a 3575. And yeah, so it is what I suspected. At 40 amps, the efficiency on these is like 86 point... What is it? Yeah, no, 89 point... Yeah, it's like 89 point... It's just under 90% at 40 amps output on these, on the MP 86905s. Whereas on a IR3575... At 40 amps output, you'd be looking at an efficiency of over 91%. So I suspect that there's just, I guess maybe the low side on these is really small or something. Yeah, I'm not entirely sure how they've managed that, but basically they have really, really high peak efficiency, and then they fall off like a lot quicker than what you'd see from some of the higher current rated parts. The reason I find that so sort of weird is that a lot of 50 amp parts are just bad, like have just a lower efficiency curve for the entire efficiency curve. There's no like really high, you know, peak efficiency and then it drops off quickly. It's more like it peaks at like because 94% efficiency for a power stage is really up there. At 1.2 volts. At higher output voltages, you can get higher efficiencies, but at 1.2 volts, 94% is amazing. And there's a lot of power stages that at 1.2 volts, like, you know, that are 50 amps nominal at 1.2 volts, they'll never hit 94% efficiency. They'll be like 93 or something. And then they'll still end up at like they'll end up in this sort of range later on in the power curve, well, in the efficiency curve. But yeah, these have a really high peak efficiency and they fall off pretty quickly. So it's kind of interesting. And yeah, I guess that's why they're nominally 50 amps instead of something higher, because they just don't work very well at the really, really high current outputs. But in the current range that you would realistically be using on a Fury at ambient, yeah, 200 to 300 amps, this is actually like really, really great efficiency right there. So that's cool. And then the documentation for these also ends at 40 amps. So unfortunately, I don't know how they perform at like 500 amps output for this VRM, but like... Considering how far they've dropped going from 300 to 400 amps, it's not going to be great. So yeah, like, which this is pretty normal for most parts to have a nominal spec that is, and then the actual documentation not going out to the nominal, like the nominal current rating, because you shouldn't be running 50 amps through a 50 amp power stage. Like, you just shouldn't do that, because the efficiency is going to be terrible. And so this is more like a performance class than it is an actual useful design parameter. because, yeah, this is like, yeah, you can technically do 50 amps. Please don't actually do that in a real-world design. Anyway, so yeah, we've got a really, like, nice VCore VRM. The main thing, like, even though these, like, drop off really quickly compared to some of the higher current rating power stages, the thing is, this is a 10-phase. Most Furies, actually, I think all Furies, max out at a 6-phase VCore. And so you don't really get, like, this is probably the most efficient VCore VRM you can get on a Fury. So, yeah, good job ASUS on that. I'm a big fan of that. Then for the HBM VRM, we're just looking at a bunch of discrete MOSFETs. So we have, you know, our high side and our two low sides. The reason you do this, the whole reason you put two low side MOSFETs in one phase is because you get lower RDS on, and that effect, like by putting them in parallel, you effectively get lower RDS on, and that gives you more efficiency. And the MOSFETs being used here for the high side, we're looking at a QM 3054 from Ubic Semiconductor. So this is actually like the same company that also makes UPI voltage controllers, just fun fact. So it's kind of weird because you have UPI, I guess they're two brands under the same company kind of thing, because UPI and Ubic, like they share a website and everything, so I guess they're like different brand names for different divisions, but yeah, so Ubic Semiconductor 3054 for the high side, and actually that's the same on the VDDCI rail. Like, these are both the same configuration. And then for the low sides, we're looking at a bunch of QM, I can't write M's today, 3056s. And so the 54 is a 4.8 milliohm MOSFET, so very low resistance. And then the 3056, like, yeah, for a high side MOSFET, that's actually a very low resistance, but ASUS has used this VRM configuration on a bunch of cards, and it works great. And also, the HBM on a Fury really doesn't pull much power. In fact, it pulls so little power that the heatsink for this GPU there's no heat sinking for these MOSFETs whatsoever. They're just kind of there, left to be cooled by the airflow from the downdraft air, from the downdraft air cooler, and it works fine because HBM doesn't pull any power. The VDDCI rail doesn't really pull any power because first gen HBM only ran at like 500 megahertz, which also means the memory controller runs at a very low frequency, which means the memory controller doesn't suck up a bunch of power. So you don't need a very big substantial memory or memory controller VRM, and you can get away with just, you know, 3 MOSFETs in like one phase for each rail with 3 MOSFETs, and then don't even need a heatsink for them, which is pretty neat. Anyway, the QM3056s are 4.2 milliohm RDS on, which is kind of high for low-side MOSFETs, but that's why we have 2 of them, right? By putting 2 of them in parallel, you effectively have a 2.1 milliohm low side there. And we're not going to talk about the efficiency on these because I don't care. There's not much, like, especially because on modern Fury, like, if you're using the latest drivers with an R9 Fury, you cannot overclock the HBM because AMD, in their infinite wisdom, broke HBM overclocking. And when, asked to fix it, they said, oh, it wasn't supposed to work in the first place. So, good job, AMD. And no, I'm not going to let that go. But anyway, so yeah, so unfortunately, like, talking about overclocking the HBM is not even very relevant because you can't unless you use outdated drivers. And the funny thing is, or outdated drivers, like, the last drivers that had HBM overclocking support was 16.12 something. Like, the 16.12 drivers are the last HBM overclocking drivers. From 17 forward, you can't overclock the HBM. Like, sure, you can move the HBM clock slider up in your Afterburner or your Sapphire Trix or whatever overclocking utility you're using, and GPU-Z will happily tell you that your HBM is at 900 megahertz or whatever. However, the actual frequency of the HBM has not increased. The performance doesn't change. You can't overclock the HBM. So thank you, AMD, for that. The neat thing is we don't need to talk about the HBM VRM because it's not like, you're not going to be exceeding the stock power draw on it because, yeah, you can't overclock the HBM. And anyway, so yeah, that's what's going on with the memory controller and the HBM rail, though I forgot to mention the voltage controller for the VDDCI. There might be some reason to raise the VDDCI on liquid nitrogen, so it's actually useful to know what controller this is. That is a 1540. From UPI Semiconductor, so UP1540. And that's just a single phase controller with integrated drivers and everything. So yeah, if you were thinking, oh, the 3598, like this doesn't connect to the 3598. This just connects straight to the MOSFETs, or more like that. There's not separate outputs for the two low sides. Like there's not separate drivers for each of the low sides. It's one driver driving both low sides at the same time. So yeah, that's what's going on with the sort of power delivery components. And yeah, I must say, I really like the VCore VRM. Those are some interesting power stages. I wonder if ASUS used them on any other cards, because actually they probably did. But yeah, because at the time, ASUS had a lot of GPUs where they had these really small power stages, and I, for the longest time, have not had any idea what they were. I guess they were all using MP86 905s. Because there's like the 980 Ti Strix, which had some kind of small power stage. I figured it was like a Vishay semiconductor part, but no, probably was these MP86 905s. But yeah, well, I guess I'll find out if I ever get my hands on a working one of those. Funnily enough, the 980 Ti Strix also has two different PCB versions. One which has these, what I'm assuming, monolithic power systems power stages, and then there's another version that uses 60 amp international rectifier power stages. Anyway, let's talk about the capacitor configuration. So for input filtering, we just have a bunch of APAC aluminum polymer cans, and 5,000 hours rated, 270 microfarads. This has quite a lot of input filtering. Actually, I think even the regular Fury X's also have kind of a lot of input filtering, though the regular Fury X's use a bunch of tantalum polymer capacitors for input filtering, because you can't get aluminum polymers in that kind of in the molded packaging with high capacitance, whereas these cans, you can get 270 microfarads in a 16 volt rating quite easily. The ones ASUS is using here are rated for 5,000 hours at 105 degrees Celsius. Also, if you're wondering how I know what brand these are, APAC has this weird logo thing, like that dot thing. Yeah, that's APAC. Anyway. So that's our input filtering, and we've got what? 1, 2, 3, 4, 5, 6. We've got 4 power stages for each, because you have the input filtering inductors over here. So basically, this inductor is blocking the switching noise from this VRM, or like this half of the VRM, and this inductor is blocking the switching noise from this half of the VRM. So we've got 4 bulk capacitors per 5 phases, which, yeah, interesting. Which, like, that's actually, like, the thing is, input filtering is hard to judge in my experience, because it's like, normally there's always so much of it that you don't have to worry about it. And this very much looks like a case of there's more than enough. It wasn't until very recently that I've run into a GPU where it's like, wait a minute, the input filtering sucks. But that GPU has way less input filtering than this does. So anyway, input filter looks solid, and then of course we have multi-layer ceramics right at the power stages for the really fast turn-on transients from the power stages, switching on and off, or more like just switching on. The switch off isn't so much of a problem. And then on the other side, for VDDCI and HBM input filtering, we have the smaller 100 microfarad APAC polymer can capacitors. And yeah, also 5,000 hours rated, and these are really low power rails, so yeah, this actually looks really overkill for these. For the output filtering, the VCore, I think, has the most overall capacitance out of any Fury I've seen, because we have all of these we have all of these APAC 820 microfarad 2.5 volt capacitors, which we have, I think there's one per phase. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, we've got one per phase of those. And then ASUS also added on these, what I suspect are Panasonic SP caps. I'm not entirely sure. I can't actually, there's no logo on these for which brand makes them. And these are 470 microfarads each. And the thing is, this style of, so these are molded polymer capacitors, and these are awesome. Really low ESR, really low ESL. Actually, you can get similar ESRs even in your cans, but the ESL on the molded capacitors is much better. And so these are really good for dealing with filtering high-speed transients. So what's actually interesting is the R9 Fury Nitro PCB goes entirely with through-hole capacitor, like through-hole CAN capacitors for its output filtering. And in my testing, it actually has worse output filtering than a reference Fury, because the reference Fury design has only a bunch of SP caps, as far as I can tell. And what's actually also interesting is the reference Fury design uses a 3-terminal SP cap, which basically the idea behind the 3-terminal SP caps, which is this right here, is that, molded capacitor with just 2 tabs, pretty low ESL. What about if it had 3 tabs, even lower ESL? So the extra tab is actually more ground, and it is another ground connection, and it further reduces the ESL. They're also really, really expensive. So the two terminal molded polymers are already pretty expensive compared to, CAN capacitors like this, especially per microfarad. These are 470 microfarads each, and each of them is probably more expensive than one of these 820 microfarad capacitors, which, that's so if you just need a certain amount of bulk capacitance and you don't care so much about having super low ESL, these are much more cost effective than these are. But if you want the best possible output filtering, then these are just better. And anyway, if you want even lower ESL, there's the option to go with these 3-terminal ones, which ASUS opted not to go with because they are really, really expensive. And I don't necessarily see a problem with. I guess we'll find out when I test it. But the thing is, ASUS did mix in, ASUS has just more capacitance, and they have a good number of, molded polymer capacitors on the output filtering of the VRM. So I actually expect this to be the best voltage regulation R9 Fury that I have right now. So we'll see when I actually hook it up to the oscilloscope. But this really should outperform the Nitro, the modified Nitro, because after I realized the Nitro was losing to the reference card, I was like, oh, well, that's not okay. Especially because my Nitro, the silicon on my Nitro is actually really good, and I really like the card, and the heatsink's great, which the heatsink on this thing, unfortunately, is not great, mostly because, ASUS actually has a full-length PCB for their Fury, whereas everybody else is using shorter designs, so they get, much thicker fin stacks, full pass-through on one of the fans. And so the Nitro, is great, except the VRM has this much cheaper output filter with only through-hole capacitors instead of any molded capacitors. And I was like, okay, well, that's not okay. So I modded that card to get it more in line with the reference design. But I think this should beat both of them. This should beat the reference design. It should absolutely wipe the floor with the regular Nitro design. And even my modified Nitro probably can't keep up with this. I'm not sure. But I really don't think my modified Nitro is going to keep up with this thing. But we'll see when I hook this up to the oscilloscope. Anyway, for the other rails, HBM, we just have some molded polymers and some multi-layer ceramics mixed in, and then over here for VDDCI we have the same thing. And yeah, the VDDCI power delivery is super weird, but it's a low power rail. And in my experience, the VDDCI just doesn't do anything on Fury, so that's fine. That doesn't matter. It just looks super weird to have your power delivery done like this. There is a benefit to actually having this because I think ASUS designed this PCB layout with LN2 pots in mind. And by not having, because on a regular Fury X, you'd actually have a VRM right in this area, which can be potentially a bit of a clearance problem for LN2 pots. By doing what ASUS did here, where, the actual VRMs are over here, and then all the capacitors here are the low profile ones, you don't have that problem whatsoever. So yeah, and this is actually an interesting thing that is somewhat noticeable on a lot of ASUS GPUs, and also very noticeable on Hall of Fame cards and Kingpin editions, where it's this area right above the core is always kept completely clear, so that LN2 pots don't have any kind of clearance issues with various tall components through-hole or just CAN capacitors in general, and then inductors as well are a bit of a height concern a lot of the time as well. Now the thing that I also want to talk about is just this right here. So these are all 0805 multi-layer ceramic capacitor footprints that I guess I wonder if there's an engineering sample version of this card where they actually populated all of these, because there is engineering sample 2080 Ti's, which have an absolutely stupid amount of multi-layer ceramics on their output in their output filtering. Ultimately, you can't actually buy a retail 2080 Ti with that configuration because it doesn't have any noteworthy effect. Like, it's very expensive to do, and it has zero real-world benefits to have that. So I guess the same, like, ASUS came to the same conclusion with this right here, but they left all the pads back on there. So if I feel like it, I guess, you know, well, the thing is, I already expect this card to outperform all of the other Furies I have in terms of voltage regulation. And if I had to guess, so the other cards that I tested, like the Nitro in its stock configuration was about 250 millivolts peak to peak. The reference design is like 190-ish, 190 to 200. If I had to guess, this is probably around 180, 160, something like that. And there's a pretty, like, there's a limit to how low you can get your peak to peak values. So, yeah, I don't think I'll bother, like, I won't try to populate all this. Like, it would be cool to have it populated, but man, I like this would take way too long, and I expect it to make no practical difference. But yeah, so it, like, though I do wonder if ASUS ever had a populated version of this, because that would look like ridiculous. Like, it still looks ridiculous. Like, wait, were you seriously going to have this many multi-layer ceramics on the output? Though it is interesting that actually the revision 2.0 version of this PCB, which we will make a video about, I guess, that actually has more SMD polymers on the output, or more molded polymer capacitors on the output than this does. So that would probably have slightly better output filtering again. You know what? Maybe I might end up, like, you know, maybe someday I'll be intensely bored and I will, I don't know, populate like this much of it. That still looks like way too much. What is that? That's like 416. That's, oh, wait. So 5, 9. Yeah, that's a lot. That's way too much. Anyway, behind the core, we actually have the reference Fury capacitor configuration, because I don't believe like ASUS is allowed to fiddle with the capacitor layout behind here. Yeah, so this is just sort of the standard multi-layer ceramic capacitor configuration that you'd see on a Fury X or a Fury, and I don't know, it probably works fine. It's hard to, like, yeah, I'm not sure that there's, like, this is hard to judge, because you don't, like, I normally just go by comparison measurements, and so here this is kind of like, well, it's multi-layer ceramics, they're directly behind the core, because that's where you need the lowest ESR, lowest ESL capacitors. So yeah, this is what you normally see on a Fury. But anyway, so that's it. That's the R9 Fury Strix PCB from ASUS, and you know, the heatsink kind of sucks on these, but the PCB is actually, at least looks really, really nice on paper. And I guess we'll see if we'll confirm if it actually works really well with the oscilloscope eventually. So yeah, that's it for this video. Thank you for watching. What else was there? Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store, where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. It would be much appreciated if you check the links out, because they help out immensely with running the channel. Yeah, that's it for the video. So thank you for watching, and goodbye.